Yeah, and ProClus is basically a three-phase algorithm. The input parameter is the number of clusters as before, and we need a second parameter, which is a kind of arcward thing. It is the average dimensionality of the subspaces, which is denoted as capital L here in the remainder. Yeah, so the number of clusters we already know from k-medoid algorithms. Okay. But the second parameter, well, it deals with the subspace search, how many relevant attributes we expect, yeah, on average, and we'll see that this somehow is used in a very coarse heuristics, because we will try, or the algorithm actually tries to generate clusters of dimensionality L, yeah, and L should be, of course, smaller than the entire dimensionality D. Yeah, but that's I think very clear. Okay, so phase one is initialization. Of course, you can initialize k-means, k-medoid clusters in many different ways. And here is yet another one. So there are, I think I told you, 1001 different ways to initialize k-medoids or k-means clustering algorithms. Here is the 1002nd one. So the idea is that we want a set of centroids which are most far apart from each other. So each centroid should come from a different cluster, meaning that we want to maximize the pairwise distances of the initial clusters somehow, cluster representatives somehow. Of course, without doing too much effort, yeah, because otherwise we could do the entire clustering from scratch, so to say. Yeah. So what we what the authors here actually try to propose, or not try to propose, they propose. Of course, we do not know which of these k points are the best, so we choose a superset here of b times k medoids. B is another parameter which is kind of a magic number, internal parameter, which is set to some specific value. So we take maybe, for example, 10 times k medoids, such that they are well separated, and that is put into the set M here. So M is a set of b times k medoids, and then we choose a random sample of a times k data points, which is denoted as S, and out of S we select b times k points by greedy selection. Yeah, so the M set, the b times k points, is drawn out of a random sample of a times k points. Yeah, so why that two-stage sampling? Actually, I have no clue. But anyway, yeah, it sounds good. Okay, so we end up in getting b times k points. So the medoids are picked iteratively such that the current medoid is well separated from the medoids that have been chosen so far. So we take the first medoid from the set of candidates here, and then we take the one that has the highest distance to this first medoid as the second medoid from the set of M, from this set M here, from these b times k medoids. Yeah, and then as a third one, we take the one that has the highest pairwise distance, or the highest distances to the first two chosen medoids, and so on and so on and so on. Yeah? So that we iteratively pick those medoids that are well separated from the so far chosen medoids that we already have. Yeah? And of course we select b times k points here, and these initial input or additional input parameters here, a and b, which actually controls the size of the sample that we use, are just introduced for performance reasons. The procedure has nothing to do with subspace or projected clustering, but could be applied to any k-partitioning algorithm. So that is, as I said before, just yet another method for initializing cluster centers. Yeah? Has nothing to do with our special setting of subspace clustering, projected clustering, whatever. That can also be applied to any other subspace clustering algorithm, and to any other k-means or k-medoid clustering algorithm, of course. Yeah. So that was phase one, initialization of cluster metoids. Second phase is the well-known iterative phase, which works similar to any k-metoid clustering, where we try to optimize the cluster memberships. Yeah? First of all, k-randomly chosen metoids from M, from phase one here, are the initial cluster metoids, and we keep M. So the set M here that we keep is the set of candidate metoids throughout the entire clustering algorithm. So the final metoids that we get will be a subset of this M here. Yeah? So we work again only with this set M here throughout the remaining phases of the clustering algorithm. Yeah? And we start with K, of course, K randomly chosen metoids from M as initial cluster centers. And then, as always in k-metoid clustering, we replace the potentially bad metoids with other points in the metoid candidate set M. Only, of course, if the quality of the clustering increases. Yeah? And to do that, actually, we use the following procedure. We find dimensions related to the metoids, then assign the data points to the metoids, evaluate the clusters that we have formed, see if it increases, actually, the quality increases, and then we try to find the bad metoids and try to improve the results by replacing these bad metoids. Well, the bad metoids are all obviously those metoids that have a bad optimization function, a bad cost, actually a high cost, a low compactness measure, and of course we try to replace those by finding other metoid candidates from the candidate set M here. Yeah? And we'll go through these different steps here of this procedure and see what actually is done in all of those steps quite briefly, actually. Yeah, but I think that the overall procedure is quite intuitive. Yeah, we find that now not only replacing metoids through non-metoids, but we now also want to find the subspace preference. Yeah? So that is the integration of the subspace search into the clustering search, into the clustering refinement. Yeah? So we find the dimensions related to the metoids, assign the data points to the metoids based on those relevant dimensions, as I said before. Yeah? So if we find for a given metoid of only 4 relevant attributes, and for another metoid we find 10 relevant attributes, then we use only those relevant attributes for assigning the data points to the metoids. But we'll see that now here in detail.